Good evening, everyone. So welcome to my YouTube channel, Network. So today we are going to see proof of Rolle's theorem. Okay. So let's start today's session now. So what is actually Rolle's theorem? Let's write a statement of Rolle's theorem. Let F close interval AB to R be a function. Okay. So here A and B are real numbers. Okay. And A is still less than B. Okay. If F satisfies following condition, following conditions. What are those conditions? Following conditions. First condition is F is continuous on closed interval AB. Okay. Second one, F is differentiable on open interval AB. Third, Fp is equal to Fb. Okay. Then and third one is Fa is equal to Fb. The functional value of F at A and B are equal. Is equal. The functional values of F on A and B are is equal. Okay. Then what will happen? Then there exists C belongs to open interval A. What does it mean? C belongs to open interval AB. It means C is in this range. Such that derivative of F at C is 0. Okay? It means derivative of F at C vanishes. Okay. So let's see its proof. So how to prove this theorem? Okay. Okay. Since F is continuous on closed interval AB, okay, we get that F attains its bounds. It means supremum and infimum on closed interval AB. Every continuous function attains its bounds, supremum and infimum on closed interval AB. Okay. Therefore, there exists x naught y naught belongs to closed interval a b such that m is equal to, we are saying, infimum fx x belongs to closed interval a b is attained on the point fx naught. Okay, sorry, x naught, and supremum is capital M. Supremum f5. Okay. Now there are two possibilities. There are two cases. There are two cases. Case one is what? Case one. What is that? M is equal to capital M. Small m is equal to capital M. Okay. In this case, then what will happen? Because you take any x, the functional value of fx, the functional value of f at x will be less than equal to m, because this is supreme, and m, small m will be less than fx for all x belongs to closed interval a b, because this is infimum. Okay, but this is m, but small m is capital M. Okay, so what we got? So we will put here, we get okay. So we get in place of small m you put capital M. This is this. So what is the meaning of this? It means fx is equal to capital M for all x belongs to closed interval A. So what is the meaning of this? It means f is constant because m is fixed. So this implies, what is the meaning of this? This implies m is constant on closed interval AB. We know that constant function has derivative 0. It means f dash x is 0 for all x belongs to closed interval A. Now you can take any x, c is equal to x. Now take any c belongs to closed interval AB open. We also have f dash c is equal to 0. So in this case, Rolle's theorem is proved. Okay. Rolle's theorem is proved. Now we come to case second. Case second. Case 2. M is not, small m is not equal to capital M. So small m is not equal to m. We always know that small m is always less than capital M. Now small m is not equal to capital M, and M is always less than equal to capital M. What does it mean? It means M is strictly less than capital M. Okay. 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 So what we have, okay, next, so, we claim that, so, because X naught, there are two possibilities, B, it is either X naught is less than Y naught, or X naught is greater than Y naught. Okay. X naught cannot be equal to Y naught, because if X naught is equal to Y naught, then small m will be equal to, so you write like that, as f X naught is small m, that is strictly less than capital M, and capital M is nothing but Fy naught. So this implies, X naught is not equal to Y naught. So X naught is not equal to Y naught. What does it mean? It means that either, so this implies either X naught is still less than Y naught, or X naught is still less than Y naught. Okay. X naught is still less than Y naught, or X naught is still greater than Y naught. Okay. Y naught. Now, so we assume that X naught is less than, X naught is still less than Y naught. Okay. And prove the theorem. Okay. Similar proof can be done. Similar proof can be carried out for the case for X naught is still greater than Y naught. Okay. So we will prove this theorem for X naught is still less than Y naught. Same proof can be repeated for X naught is still greater than Y naught. Okay. So what we have this. So we have x naught is to be less than y naught. Okay. Okay. So what we have actually, we have fx naught, that is small m. Okay. So f a will be greater than this, and is equal to this f b. Okay. And then we have capital M, that is fy naught. Okay. So this implies since 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 m is still less than capital M, we cannot have x naught is equal to a and y naught is equal to b. So this case is not possible, because if this case is possible, then small m and capital M will be equal. That is not possible. So this case is not possible means what? We cannot have x naught is equal to a and y naught is equal to b. What does it mean? It means either x naught is not equal to a. Okay. Okay. So what we have, this case is not possible. So either x, so this implies x naught is not equal to a, or y naught is not equal to b. Okay. Now we'll take this as sub case. Suppose x naught is not equal to a. So consider this sub case. Sub case 1. X naught not equal to a. Okay. So if x naught is not equal to a means, and we know that x naught, okay, so x naught not equal to a. So we came to know that x naught not equal to a. Okay. And we also, so what is the meaning of this? So we have this case, x naught not equal to a means what? We have, so this implies a is less than x naught, because x naught is point in closed interval a b. Okay. So it is not equal to a, because x naught belongs to closed interval a b. So this implies here x naught is satisfy this condition, but this is not equal to a. It means this case will happen. Okay. And we also have that x naught is to be less than y naught, and y naught, because y naught also belongs to closed interval a b. So this implies y naught less than b. Okay. So what we have? We have that x naught is p less than b. So this implies x naught is in between a and b. So from here and from here we have this one. Okay. function is differentiable. Now, what is the now take sorry. Now what is limit? So what is put? So what is derivative? So f dash x naught. What is this? If we take left right hand derivative, so what is this? But fx naught is minimum point. Fx naught is minimum point because fx naught will be greater than equal to small m, that is fx naught. So this part will be fx naught plus h minus fx naught will be greater than equal to 0. And h is also positive because we are approaching from right hand side, from positive direction of 0. So limit will be non-negative and derivative exists. That is why this limit is non-negative. So this implies f dash x naught is non-negative. Let's see this equation number 1. Now, also, and if we take left hand derivative, okay. So what we have here again, fx naught plus h that is equal to fx naught, okay, because this is minimum, okay. So this implies fx naught plus h minus fx naught is greater than equal to 0. But h is negative. This part is non-negative and this part is negative. So resultant will be negative, non-negative. So this is less than 0. So from 1 and 2, what we have from equations 1 and 2, from 1 and 2, we have from 2 what we have, from 2 we have that, okay, from 1 what we have derivative is non-negative, and from equation 2 what we have derivative is non-positive, okay. So what is the meaning of this? This is f dash x is 0, okay. Put c is equal to x naught, okay. Then C belongs to open interval A, B. This means C lies between A and B such that derivative vanishes. Article f dash at T is equal to 0. So this implies in this subcase Rolle's theorem is True. Okay. Now take second subcase. Subcase second. Case 2. Okay, subcase 2. It means y naught is not equal to b. If y naught is not equal to b, so this will imply that y naught will be strictly less than b, because y naught belongs to closed interval a b. So this implies y naught is less than equal to b. But y naught is not equal to b. What does it mean? It is still less than b. Okay. Now x naught is still less than y naught. Okay. Because x naught belongs to closed interval a b. So this implies a is less than equal to x naught. So this implies a less than equal to y naught. Okay. So this implies, okay, from this and from this, what we have? We have this implies y naught lies between a and b. Now, next, what is derivative at y naught? This is equal to, you take right hand derivative, then what will get? S tending to 0, fy naught plus h minus fy naught upon h. Okay, because fy naught is maximum, so fy naught plus h less than equal to m, that is fy naught. So this implies fy naught plus h minus fy naught is less than equal to 0, and h is positive. Then what is the resultant limit? Resultant limit will be, what will be? Non-positive. Okay. Non-positive means it can be 0 or negative. Okay. To positivity. That is, it is non-negative. So this implies f dash y naught is less than equal to 0. Equation number 3. And what we have, now take left hand derivative. F dash y naught equal to limit h stands to left side of 0. So this was the positive direction. Then what you will get? Okay. This is fy naught plus h minus fy naught upon h. Okay. Here, fy naught plus h minus fy naught is non-positive and h is negative. So what resultant you will get? This will get positive, non-negative, sorry. So this is f dash y naught greater than equal to. That says 4. So from 3 and 4, what you have? From equations 3 and 4, from equations 3 and 4, we get this is from equation 4 and this is from equation 3. So what you got? What is the meaning of this? This means fy naught derivative fy naught is 0 actually. Okay. So now take put c is equal to y naught, then c C belongs to open interval AB. It means C lies between A and B, such that f dash C is equal to 0. So in this case, in this subcase, Rolle's theorem is proved. Okay. So in all the cases, Rolle's theorem is proved. In all the cases, Rolle's theorem is proved. So hence, Rolle's theorem is proved. Okay. So Rolle's theorem is proved now. So physical interpretation of Rolle's theorem. Physical interpretation of Rolle's theorem. So what is the physical interpretation of Rolle's theorem? So we have a continuous function on closed interval AB. So we have this coordinate system x, y. So there is a closed interval AB, and we have functional value same on both the points, and there is a continuous function and differentiable on open interval AB. So this function will be look like something like that. Okay, this is fk value and this is fp value. So this says there will exist a C point, at least a point C here, where derivative will be 0. Okay. So what is this? This will be f dash C will be 0. So this is the meaning. It means if you have a continuous function on closed interval AB and differentiable on open interval, there will exist a point C in between. C is in between A and B. We have the slope of tangent at C, that is f dash C, f dash evaluated at C will be 0. It means derivative of f at C will be 0. It means the slope of tangent on the curve, this curve at C will be 0. Okay. So this is the physical interpretation of Rolle's theorem. Okay. So related to this, if you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you next lecture.